Hey everyone, welcome back to the channel. I'm Vaibhav, and today we're diving into something that most people completely skip over, the assumptions behind linear regression. Think of these as the fine print that tells you when linear regression will work brilliantly and when it'll completely fall apart on you. This is one of those topics that separates beginners from people who actually know what they're doing with their models. If you've been following this series, that subscribe button really helps us keep creating content like this. Here's the thing, linear regression isn't magic. It only works properly when your data meets certain conditions. Break these rules, and your beautiful model becomes about as useful as a chocolate teapot. Let me walk you through the 5 key assumptions using our car data set, and more importantly, show you what happens when things go wrong. Assumption number 1, linearity. This means the relationship between your features and target should actually be a straight line. Look at our car age versus price data. As age increases, price decreases in a nice straight pattern. That's perfect linearity. But what if depreciation actually accelerated after year 5? Then you'd see a curve instead of a straight line, and linear regression would give you garbage predictions. How do you check this? Plot your features against your target and look for curves. If you see banana shapes or S curves, linear regression isn't your friend. Assumption number 2, independence. This one's sneaky. It means each data point should be independent of the others. In our car example, this would be violated if we included multiple cars from the same owner or cars sold on the same day when market conditions were weird. Basically, one car's price shouldn't influence another car's price in your dataset. This gets tricky with time series data. If you're tracking the same car's value over multiple years, those data points aren't independent. They're connected. Assumption number 3, homoscedasticity. Don't let the fancy name scare you. It just means your errors should have consistent variance. Here's what I mean. Look at our prediction errors across different price ranges. For cheaper cars, we might be off by plus or minus $500. For expensive cars, maybe plus or minus $2,000. That's totally fine, as long as the spread is consistent within each price range. But if cheap cars have tiny errors and expensive cars have huge wild errors, that's heteroscedasticity, and it breaks our assumption. Your model becomes unreliable, especially for predictions at the extremes. The quick check, plot your residuals against predicted values. You want to see a random cloud, not a funnel shape. Assumption number 4, normality of residuals. Your prediction errors should follow a normal distribution, that classic bell curve shape. This doesn't mean your car prices need to be normally distributed. It's the errors that matter. Most errors should cluster around 0, with fewer large errors on either side. Why does this matter? Because all those confidence intervals and statistical tests we use depend on this assumption. Break it, and you can't trust any of the statistical inference your model gives you. You can check this with a histogram of your residuals or a QQ plot if you want to get fancy. Assumption number 5, no multicollinearity. This means your input features shouldn't be too highly correlated with each other. In our car example, imagine if we included both car age and years since manufacture. Those are basically the same thing. When features are too similar, your model gets confused about which one is actually driving the predictions. The fix, use correlation matrices to spot highly correlated features, then pick the most relevant one and drop the others. Now here's what's really important. What happens when you violate these assumptions? Break linearity, and your predictions will be systematically wrong in predictable ways. Violate independence, and your confidence intervals become meaningless. Mess up homoscedasticity, and some predictions become way less reliable than others, but you won't know which ones. Ignore normality of residuals, and all your statistical tests and confidence intervals go out the window. Have multicollinearity, and your model becomes a black box where you can't trust the individual feature coefficients. So, how do you fix these problems when they come up? For nonlinearity, try transforming your features. Sometimes the solution is admitting that linear regression just isn't the right tool. For independence issues, be more careful about your data collection. For heteroscedasticity, you can transform your target variable or use weighted regression that accounts for different error variances. For non-normal residuals, again, transformations often help. For multicollinearity, just remove the redundant features or use techniques like principal component analysis to combine correlated features intelligently. Here's the reality check though. Real-world data almost never perfectly meets all these assumptions. Sometimes minor violations don't hurt your predictions much. The key is learning to diagnose these issues and knowing when they're deal breakers versus minor annoyances. In our next video, we're finally getting our hands dirty with code. If this deep dive into assumptions helped clarify when linear regression works and when it doesn't, smash that subscribe button. I bet assumption violations were probably the culprit. Thanks.